Hi, and welcome to this first video in a sequence of videos on support vector machines. So in this video, I'll try to just motivate what support vector machines are. Okay, so to motivate them, let's go back to something we saw in one of the very first videos. We looked at this perceptron learning algorithm as a first example of a learning algorithm. And the perceptron learning algorithm, what we worked with was the binary classification case. The labels were -1, +1, and we have feature vectors consisting of D features and a hard-coded one to take care of a bias. And in general, in this perceptron learning algorithm, it trains a linear model. And in such a linear model, we have a parameters in a vector W consisting of D+1 parameters, one for the bias and one for each of the input features. And the predictions that you make using the perceptron learning algorithm, if you have a feature vector X and you want to make a prediction of the corresponding label, then you take the sign of the inner product between X and the vector parameters W. Right, so this is something we've seen before for a while back. Now, what we saw was the perceptron learning algorithm is an algorithm for finding a good set of parameters W. And by good, we mean that it classifies most of the training data correctly. And then we hope, of course, that this means that we also have good performance on new data. And this is what we've seen in many of the learning theory videos. We already argued that this is often the case, that good performance on training data implies good performance on new data, at least if you have enough data. And if the VC dimension or the complexity of the hypothesis set is not too large. Right, and we saw that this perceptron learning algorithm was a really simple algorithm. So if you have your data with features x0 up to xd, labels -1, +1, the algorithm was just initialize W, just say to all zeros, and then you say, while there is a data point that is currently misclassified, right? So you look at the current prediction, compute the sign of the inner product, you compare it to the true label, and if there's one that's mispredicted, then you update your W by adding the label times X to W. And the basic idea that we also looked at earlier was that this, in some sense, makes W more correct, at least on this misclassified example, X, Y. And then at the end, when there are no more points left that are misclassified, you return W. So just as an example, right? The triangles, the red triangles have labels -1, and the blue circles have labels +1. If you're in some iteration, this is your current vector W of parameters, you look for a misclassified point. And for instance, it could be this one here. And then you say, okay, I need to update my W. I see that this is the feature vector X, the vector that goes to this point. And now the label is -1, so I have to add -X to W. So I change my W to be this vector here instead. And now this is my new hyperplane. And you can see that now we've classified the red point correctly, right? So this was the basic idea in the perceptron learning algorithm. Right. And of course, right, this change may make it wrong on some other points, right? So maybe it fixes this one mistaken point, but it may introduce mispredictions on other points. And while it's not obvious at all, one can actually prove that if the data is linearly separable, meaning there is actually a hyperplane that separates the data into the two classes, then this is actually going to terminate with a perfect classification of the training data, which is not at all obvious. And this is not so trivial to prove as well. So linearly separable just means that if I have data, then it's linearly separable if I can draw a line or a hyperplane that separates the two classes onto above and below the hyperplane. Right, so this is linearly separable. And now we've kind of gotten to a point where we can try and motivate support vector machines, right? So the one thing you could ask is, are all separating hyperplanes equally good for classification? For instance, you have this, say we have this data here, right? The red triangles and the blue circles. And we have to make a classification on these new points, the green ones that we have here. And just looking at the picture, it could seem like, the bottom one here is probably blue and the top one is probably red. But this is a completely valid separating hyperplane for the data, right? So this hyperplane here does have all the blue on one side and all the red on the other side, but it kind of makes the prediction that we don't find natural on these 2 points here, right? It would predict red on the bottom one here and blue on the top one here. And this is not really what we believe is the right prediction, at least just by looking at it with our eyes. So at least in this picture, it could seem like this hyperplane here is better in some sense, right? It looks better. And so the question is, can we make this formal? Can we say, why is this hyperplane better? And the reason why it looks better is that somehow there's a large margin until you get to the training data. Like around this hyperplane, there's a large strip that's completely empty. There are no training examples in here, right? So they're sitting quite far away from the hyperplane. This was not the case with this other hyperplane up here, right? The margin is really small. This example up here is very close, and this blue example here is very close as well. So, but here we have really large margins to the data. So this is something that we like. There are large margins to the data. And also, if we think about, say, logistic regression, maybe the thing with large margins is also apparent in something like logistic regression. So in some sense, right, logistic regression, if you look at this returns probabilities of being in the two classes, and for logistic regression, the probabilities you output are also kind of more certain on points that are far away from the hyperplane, right? If you're very close to the border, you're more like 50-50 between the two classes. And if you're far away, then you get either closer and closer to estimating the probabilities 1 of being in the class 1, or the probability 0 of being in the class 1. So, so some sense, but there's also a notion here, or at least an idea that, well, if you're very far away from the hyperplane, then you're more certain on your predictions. That's at least the intuition that one could have. So in support vector machines, basically what they do is that they are going to find the hyperplane that has the largest margin to the training data. Right. And of course, right, if the training data is not linearly separable, and it doesn't even exist, right? There's no hyperplane that has any positive margin. So for now, we'll just start by assuming that indeed our data is actually linearly separable, and we'll return to how we can deal with this later. Okay. So let's try to formalize what these margins are, this gap to the nearest point. And to do so, right, I'll just remind ourselves that when we have a hyperplane, it's specified typically by a vector, a normal vector, maybe not normalized to have unit length, but a vector W that's orthogonal to the hyperplane, and then also a bias B, where the bias is the offset in some sense from the origin in the direction of W. Right, so B is in some sense an offset, and W is orthogonal to the hyperplane. Right, and the points on the hyperplane here are exactly the set of points x, such that the inner product between x and w plus b is equal to 0. Okay. So, right, so here for support vector machines, we're not going to hide the bias by hard coding it into a feature. Here we're actually going to keep the bias separately, and this is unfortunately necessary and important. So the bias we will have to actually deal with explicitly here. Okay. So in some sense, if you look at this inner product, if you take any feature vector x, and I look at this inner product with the vector w and add the bias, then this value gives the assigned distance from the hyperplane. So here, for instance, you can see that, well, if you're exactly on top of the hyperplane, we already know those are the points that have, where this is equal to 0. And below the hyperplane, right, this is where you make negative predictions. These are negative numbers, and they go out linearly as you go further away. And up here above the hyperplane, they're positive, and they scale by the distance as well. So in some sense, this inner product is assigned distance up to some scaling. So this motivates what's called functional margins. Okay, so when we have a training example xi with label yi, then we define the functional margin gamma I hat as the label yi times, I guess, the signed signed distance from the hyperplane, but not really normalized. So we'll get back to what that means. But basically, we just take this inner product between xi and w, add the bias, and multiply it with the label yi. This is what we call the functional margin. And then what we do observe is that, well, this functional margin is positive if the training example is on the correct side of the hyperplane. Why is that? Right, because if it's on the correct side of the hyperplane, then the sign of this prediction, w's inner product with xi plus bias, the sign of this must be the same as yi, so meaning either they're both positive or both negative. So their product is in particular going to be positive in this case. On the other hand, right, if the sign is opposite between the label yi and this prediction here, then the prediction you would make would be negative, or would be wrong, and the product of the two would be negative because they're either +1 -1 or -1 +1. So functional margins, we like them when they're positive, right? So in particular, right here on this side of the hyperplane, right, these are all the points x, such that this inner product between w and x plus the bias is greater than 0, and these up here are points x where the inner product between w and x plus the bias is less than 0. So these are the ones that are supposed to be predicted red, and these are the ones that are supposed to be predicted blue. And then we just define the function margin when we have the functional margins. The function margin is just the smallest margin the smallest of all these functional margins on all the training examples, right? So it's just saying the one that has the minimum margin. Okay. And the basic idea in support vector machines is that what we want to do, in some sense, it's not the final formulation, but the intuition is that we would like to find parameters W and B, so find the parameters of the hyperplane, to maximize this functional margin, or the function margin in particular. We want the smallest margin to be large, the smallest distance, the hyperplane to be large. Now, the problem with this formulation up here with the functional margins is that, well, that several hyperplanes that are the same. In particular, if I scale W and B by a factor 2, then I get the same hyperplane, right? Because it's exactly the same set of x's that satisfy this equality, right? You can see you just multiply both sides with 2, so 0 times 2 is still 0, and the left-hand side has just been scaled by 2. So they represent the same hyperplane. But if you look at what is the functional margin on a training example, if I scale it up by a factor 2 here, I scale up the bias by a factor 2, I can see that I can pull the factor 2 outside. And what I've just done is I've just increased the functional margin by a factor of 2, which means that if I'm trying to optimize or maximize the function margin, basically the optimization algorithm, if you just let it try to optimize this, it's just going to put infinitely large weights on it, right? Because as soon as I found something that's has all the signs correctly, so all the functional margins are positive, then if I just upscale that hyperplane, scale the W and the B by the same huge factor, it just gets all the functional margins just get larger and larger and larger. So this formulation doesn't quite work. So maybe let's take a step back and remind ourselves, what is it that we're really interested in? Like, what we're really interested in is that we want to maximize the distance to the hyperplane, not necessarily these functional margins, right? We just want the actual distance to be as large as possible. So to do so, right, what we'd like to do is, at least first, we guess we have to understand, given a point X, what is its distance to the hyperplane, right? So the closest point on the hyperplane is, of course, the orthogonal projection of the point onto the hyperplane, right? So you just move in the direction of W until you hit the hyperplane like this. So this is the closest point. And so this means that, okay, so this is some scaling of W that you move towards to get to the hyperplane. So the projection of X is actually the true vector X minus some scaling times W, right? So some scaling times the vector W. Right, so this is what we have here. So this is delta times W. So this vector here, delta times W, this is really what we're interested in figuring out. What is the formula for this delta times W? How large is delta? You know, how far away did we move when we project X onto the hyperplane? So just to get a formula for it, right, we know that this point here, the projection has to lie on the hyperplane, right? That's the definition, right? So it's moving in this direction and it has to lie on the hyperplane, which means that it must satisfy this equality here that X minus delta W, giving us this point here, has to lie on the hyperplane, meaning that W transpose X minus delta W plus B has to be 0. Okay. So, right, and what we also know is that the actual distance here, right, is really the length of this vector, right? And this vector is the delta W vector, and so its distance, or the length of it, is delta times the norm of W. And here I'm keeping a sign, so if delta is negative, it's going to be a negative distance. Right? You could also have taken absolute values in delta if you just wanted the distance to the hyperplane. But basically, this just follows by the length of a vector, right? The scaling factor delta just scales the length by that amount, and then you just have the norm of W. So let's try to figure out what is this distance to the hyperplane, right? And we can compute this just from knowing that it satisfies this equality here. So I just look at this equality, and then I work with it, and I multiply the W into the parentheses, right? So the W transpose X, and then we have W transpose W, which is the squared norm of W. We have our delta, we have our B. Okay. What I do now is I take this whole expression and I divide by the norm of W. Right, so I'm just going to assume that it's non-zero. Okay, so what we get here is that the first term is divided by W, one of the squares goes away, and the second one also divides by W. And now we can see that if we move this to the other side of the equality, the delta W term, then we get an expression for delta W being W over norm W inner product X plus B over norm W. This is the signed distance to the hyperplane. So this is exactly a formula for the sign distance to the hyperplane. Okay. So this motivates what we call geometric margins, which are the ones that we really care about. So the geometric margins here without hats on, so these are just gammas. The geometric margin for the ith point is you take the label of that point, and then you multiply it with this sign distance to the hyperplane. So you take W and normalize it by norm W. You take the inner product with xi, and then you add B over norm W. This number here you multiply with yi, and this notion of having a sign distance, the whole purpose is that you can still tell whether you're on one side of the hyperplane or the other side of the hyperplane. So for the positively labeled vectors here, you get a positive margin if your label is 1, if this inner product is, and plus the bias over W is also a positive number. So what you're really interested in is now we want to have the largest possible geometric margins. In particular, we want the smallest one of them, the minimum over all the training examples. We want this one to be large, right? Because that's the final margin. That's the minimum over all these training examples, right, of their sign distance to the hyperplane. Like you see, this point up here has a much higher sign distance to the hyperplane than this one down here. Right? So it's the minimum over all the points that we want to maximize. And the nice thing here is that this is scale invariant on the scalings of W and B, right? So if you upscale W and B by a factor 2, then you've upscaled W by a factor 2, so it's killed again by the norms have canceled it out. So this is really scale invariant, this notion of geometric margins, which is what we like. Okay, so support vector machines are really all about solving this following constraint optimization problem. You want to maximize the geometric margin gamma over the choice of W, B, and gamma. And the constraints that you have to satisfy is that for all the n training examples, the geometric margin, or here actually we're saying that the functional margin, so we're not dividing by norm of W, we're saying this has to be at least gamma. And then secondly, we have another constraint that just says, well, the norm of W should be 1, which means that the geometric and functional margin are the same. All right, so if we solve this optimization problem, then we are really maximizing the smallest geometric margin, right? The smallest distance to the hyperplane. And with a sign included in that, you have to say you actually have to put the points on the correct side of the hyperplane as well, right? So the yi, this yi times this prediction has to be positive. They have to have the same sign. So this is the support vector machine formulation in its simplest version. Now, there are a bunch of issues with this formulation. That means that we can't just take our favorite convex optimization problem solver and try to solve it. In particular, this last constraint is not really a convex constraint. So we have to return to that, and that's what we'll do in some of the next videos. We'll try to look into how to solve this optimization problem.